Hello my dear students. So in my last class I was explaining about what is meant by entropy, and we also derived an expression for entropy from Carnot cycle. So there the Carnot cycle explained that we observed two paths, that is path 1 and path 2. Okay, so that path explained was A to B and B to A. So here it was a reversible cycle, and it consisted of A series of Carnot cycle, and we derived an expression where we proved that the entropy change during the change from A to B along the path 1 or path 2 are same. Okay, so there was no entropy change observed, and even if infinitesimal, that is very extremely small amount of change in entropy was observed, so that was equal to path 1 and path 2. Okay, so that means in other words, the entropy change is independent of the path taken, and hence it was considered as a state function. Okay, so this is what the Carnot cycle explained. With the help of the Carnot engine, we proved that the entropy is a state function. That means it is independent of the path taken, and the path which has been absorbed by the example was equal, and therefore we proved that entropy change is independent, and hence it considered as a state function. Okay, and further we also saw that physical meaning of entropy by taking two different concepts, that is entropy as a disorder and entropy and available energy. Okay, so with those two concepts we took some examples, that is in solids, so how the arrangement of atoms or molecules is seen. Okay, so the arrangement of molecules or atoms in solids are regular way, having a extent, that is a perfect crystal lattice. The arrangement of the atoms and molecules will be in a perfect crystal lattice manner, that is a regular way. So when the solid is melted, so the particles forming the lattice become free. Okay, so when the lattice is going to become free, so there the disorder is going to increase. So that is because the regular way of arrangement of atoms and molecules are going to disorder. That means the order is lost. Okay, hence the entropy increases during melting of solids. So this was one beautiful example which explains that entropy and disorder, and thereby we can understand the physical meaning of entropy. In the same way, we saw how the available energy is going to used to understand the meaning of the entropy. Okay, so entropy, which is regarded as a measure of unavailable energy. So when entropy S is multiplied by the temperature T, so the product Ts is the amount of unavailable energy which cannot be converted into useful work. So that is why so the available energy, which is called as X, can be put as X is equals to Q minus Ts, or Ts where the Ts will represent the available amount of heat which can be converted into a useful work. Okay, so this is how we understood the physical meaning of entropy. Further, we also saw that entropy change of an ideal gas with the change in pressure, volume and temperature, that is variation of entropy with the volume and pressure, and variation of entropy with the pressure and temperature. So this is where we stopped in our last class, and in this session we are supposed to start with the explanation of entropy change of an ideal gas in different processes. Okay, so the different process what we are going to see here is a isochoric process. So isochoric process is a process in which the volume is kept constant. Okay, and next is isobaric process. So for an isobaric process, so pressure will be equal, that is P1 will be equal to P2, and we are going to see the entropy change during an isothermal process. So in isothermal process the temperature will be kept constant, that is T1 will be equal to T2, and in the same way the entropy change during an adiabatic process. Okay, so here no heat is exchanged between the system and the surrounding, so such type of process is called as adiabatic process. Now we will see one by one. So entropy change during an isochoric process. As I told, if the process is isochoric, then it takes a constant volume. Okay, so it takes place at a constant volume. That means V1 will be equal to V2. Then from the equation 8, now you have to see what is equation 8. Okay, so this is equation 8. Okay, so this derivation we derived in the variation of entropy with the volume and temperature. So we have to consider this equation, that is delta S, which is equals to CV ln T2 divided by T1 plus R ln V2 divided by V1. Okay, so in this since V1 is equals to V2, so I can write the equation 8 in this form, that is delta S is equals to CV ln T2 divided by T1. Okay, next so this is further derivated as so delta S is equals to 2.303 CV log T2 divided by T1. Okay, so this is because in spite of ln we are going to use the logarithmic derivation, so we are going to convert the ln into the log, then it takes the form 2.303 CV log T2 divided by T1, and let me call this equation as 12. Okay, so this equation gives us the entropy change during an isochoric process. That means isochoric process is a process where the volume is kept constant, that is why V1 is equals to V2. So if we substitute this value in equation 8, we are going to get delta S is equals to CV ln T2 divided by T1, and then I am converting this ln into the logarithmic form. So I am going to get 2.303 CV log T2 divided by T1, and this equation is called as equation number 12. And next is entropy change during an isobaric process. So as I told, for an isobaric process, so pressure is kept constant, that is P1 will be equal to P2. Okay, so there is no change in pressure. Hence from equation 11, so we have to consider equation 11. So this is the equation 11. So this is the variation of entropy with pressure and temperature. Since we have kept pressure as constant, since this is a isobaric process, I am going to use this equation. That means delta S is equals to Cp ln T2 divided by T1 plus R ln P1 divided by P2. So here both P1 and P2 are equal. They are constant. So that is why I am going to get delta S is equals to Cp ln T2 divided by T1. Okay, so since P1 is equals to P2, so this equation, so here this takes the form delta S is equals to Cp ln T2 divided by T1, and just like how we have converted this ln into the logarithmic form, so we are converting it. So delta S gives us 2.303 Cp log T2 divided by T1, and let me call this equation as equation number 13, and this equation is the entropy change during an isobaric process. And the third different process what we are going to see is in the isothermal process. So isothermal process means, so here temperature is kept constant, that is T1 will be equals to T2. So hence from the equation 8, okay, so we are going to take the equation 8 same way. So this is equation 8. So here temperature is kept constant. So that means T2 will be equals to T1. So that is why this equation takes the form delta S is equals to R ln V2 divided by V1. Okay, so R ln V2 divided by V1. Next, converting that equation, it will take the form delta S is equals to 2.303 R log V2 divided by V1. This is equation number 14, so which is entropy change during an isothermal process. Okay, so alternatively from equation 11, So we can because since the equation 11 is also a variation of entropy with the pressure and temperature. So here in this if we take the temperature as constant, T2 divided by T1 will be the constant. So alternatively we are going to get delta S is equals to R ln P1 divided by P2. Okay, so R ln P1 divided by P2. Therefore delta S will take this form. So let me call this equation as equation number 15. Okay, so this is we can assign two different equations for the entropy change during an isothermal process. That is so by taking equation number 8 and also by taking equation number 11, so we can get the change in entropy, that is delta S values. Okay, so these two equations describes the entropy change during an isothermal process. And the fourth type of entropy change of an ideal gas is a change of entropy during an adiabatic process. So during an adiabatic process, no heat is exchanged between the system and the surroundings. So therefore, so dq, that is the net amount of work done or the change of work which has been taken is equals to 0. And we have ds, that is entropy change, is equals to dq divided by T. So since dq is equals to 0, so therefore ds also will become 0. Okay, so if you substitute the value of dq here, so then ds will become 0. Thus during an adiabatic process the change in entropy is 0. Okay, so no entropy change is absorbed in an adiabatic process because here no heat has been exchanged between the system and the surroundings, hence the work done will be equals to 0. So when work done is equals to 0, then the change in entropy will also become 0. So that is why during an adiabatic process the change in entropy will be a 0. Next, so let us consider irreversible process, how the entropy change in an irreversible process is calculated. Consider an isolated system containing two bodies, that is A and B, at temperature T1 and T2. Okay, so A will have T1 temperature and B will have T2 temperature. So this is the two bodies are in an isolated system. So let an amount of heat dq be radiated by A at the higher temperature T1 and B at the lower temperature T2. Okay, so this is the experimental setup. So here A body is kept in the higher temperature and the temperature is called as T1, and B body is kept in a lower temperature. So both are in the isolated system, but A is in the higher temperature system and B will be in the lower temperature system. So the lower temperature is symbolized as the T2. So the entropy change of A is minus dq divided by T1, since the heat absorbed by A is minus dq. Okay, so since this is in the higher temperature, A body is in the higher temperature, so here it is absorbed. So since B is in the lower temperature, so heat is evolved or given out in B body. Okay, so that is why I am going to write the entropy change in this way, that is minus dq divided by d1 for A and dq divided by d2 for B. Now total change in entropy of the system during this spontaneous irreversible process is equal to the sum of the entropy changes in A and B. Okay, so thus the change in entropy delta S is equals to, so we have to sum up the entropy change which has been taken in two different bodies, that is A and B. So here the entropy change is minus dq divided by T1 plus dq divided by T2. Okay, so if I rearrange this, so I can get dq divided by T2 minus dq divided by T1. Okay, so I have just interchanged this, sign interconversion has been taken here. So I am going to get dq divided by T2 minus dq divided by T1. Since T1 is greater than T2, okay, so here I have told T1 is in a higher temperature, T1 is called higher temperature and T2 is the lower temperature. Since the temperature T1 is greater than T2, so delta S, that is entropy change, is a positive. Thus during an irreversible process, entropy of the system increases. Okay, so entropy of the system is going to increase. Similarly, so entropy change in a irreversible isothermal process. So now let us consider an isothermal reversible expansion of an ideal gas at a temperature T. During the expansion, let an amount of heat dq be absorbed by the system from the surroundings. Okay, so the system is going to absorb certain amount of heat which has been called as dq from the surroundings. Hence, the change in entropy of the system is dq divided by T. Okay. At the same time, heat lost by the surroundings is Q, or heat gained by it is minus Q. Okay, suppose if the heat is lost means it is symbolized as Q, small letter Q, or if heat is gained, then it is written as minus Q. Entropy change in the surrounding is minus dq divided by T. So hence the total entropy change of the system and the surroundings, that is delta S, is equals to dq divided by T plus minus dq divided by T, which is equals to 0. Okay, so this is how I am going to represent the entropy change in a reversible isothermal process. In other words, the entropy remains constant during a reversible process. Okay, so there is no change in entropy. The entropy is going to remain constant in a reversible isothermal process. Okay, so these are the different cases what we are going to see in change of entropy change of an ideal gas in different process. Next is entropy change in physical processes. Okay, so here we are going to see 4 different entropy change in a physical process. That is, one is entropy change in vaporization process, and second one is entropy change in sublimation process, and entropy change in fusion process, and entropy change in a transition process. Okay, so these are the 4 different physical processes which we are going to study now. Okay, so the entropy change in these 4 physical processes are studied in this way. Okay, so let us see one by one. Entropy change in vaporization process. So a liquid changes to vapor at the boiling point of the liquid. Okay, so this is the general phenomena. So the liquid changes to vapor. That is what is called as the boiling point of a liquid. So when the boiling point is reached, say for example, if I take water, so water will be in the liquid state till it attains 100 degrees centigrade. Once 100 degrees centigrade is attained, and if we go on increasing the temperature of the water, so then it is converted into vaporization, or then it is converted into a gaseous state. Okay, so that is what a liquid changes to vapor at the boiling point of the liquid. So in this process, entropy change increases. Okay, so this is what we studied in our last class while seeing the physical meaning of the entropy. We took the example of solids, where in all solids the ions, atoms or molecules are arranged in a regular way in the form of a lattice. When the solid is melted, the particles forming the lattice become free. So order is lost and disorder increases. Hence, entropy increases during melting of solids. This is the continued part. So, when solid is converted into liquid, if we go on increasing the temperature, so then the liquid is also going to change its state to vapor at the boiling point of the liquid, and in this process entropy change increases. So entropy change in vaporization process is calculated as follows. So delta S, that is entropy change, is equals to delta HV divided by TB. Okay, so where delta HV is the molar heat of vaporization or enthalpy of vaporization. Okay, so here delta HV is called as the molar heat of vaporization or enthalpy of vaporization, and it is measured in terms of kilojoules per mole, and TB is the boiling point of the liquid. Okay, so this is how we are going to study the entropy change in the vaporization process. So here we have to note down 2 points, that is, in vaporization process delta S is calculated as delta S is equals to LV divided by TB, where LV is called latent heat of vaporization and it is measured in kilojoules per gram. Okay, so the latent heat of vaporization or the change in latent heat of vaporization delta HV is equals to LV into molecular mass. So if we calculate, or if you multiply the latent heat of vaporization into the molecular mass of the compound, so I am going to get the change in HV. Okay, and the next point is, if vapor condenses to form a liquid, entropy decreases. Okay, so this is vice versa. Okay, when the liquid changes to vapor at the boiling point of the liquid, so entropy change in the vaporization is going to increase, and when the vapor again condenses to form a liquid, so again the entropy is going to decrease. Okay, and the next physical process is a entropy change in sublimation process. A sublimation process means, so what happens here, a solid directly changes to vapor state at the sublimation temperature. That means, so here no liquid state is absorbed. A solid directly it will change its state to vapor state. In this process, entropy increases. Entropy change in sublimation process is calculated as follows. So delta S is equals to delta Hs divided by Ts. Okay, so just like how we have calculated the entropy change in vaporization, so we are going to calculate the entropy change in sublimation process also. So entropy change delta S is equals to delta Hs divided by Ts. And here delta Hs, so this is delta Hs, this is not delta Hv, this is delta Hs, is the molar heat of sublimation or enthalpy of sublimation. Okay, it is measured in terms of kilojoules per mole, and Ts is the sublimation temperature. In the same way, here also we are going to note down one point, that is entropy change in sublimation process is also calculated as delta S, which is equals to Ls divided by Ts, and where Ls is the latent heat of sublimation and it is measured in kilojoules per gram, and change in latent heat of sublimation is equals to Ls into molecular mass. Okay, so molar heat of sublimation delta Hs is a molar heat of sublimation is equals to latent heat of sublimation into the molecular mass. Okay, so here also observe this one. So delta Hv means molar heat of vaporization. So molar heat of vaporization is equals to LV, that is latent heat of vaporization into the molecular mass. Okay, next physical process is entropy change in fusion process. A solid changes to liquid at the fusion temperature, and that is what is called as a melting point. Okay, so a solid, when it is heated or when the temperature is raised, it changes its state to liquid at a fusion temperature. During this process, entropy change is calculated as delta S is equals to delta Hf divided by Tf, where delta Hf is the molar heat of fusion or enthalpy of fusion, and it is calculated, or it is measured in terms of kilojoule per mole, and Tf is the fusion temperature. Okay, and the next fourth physical process is entropy change in transition process. A solid substance undergoes a change from one crystalline form to another at the transition temperature, and it is called transition process. Okay, so our transition process is a process where a solid substance undergoes a change from one crystalline form to another crystalline form. Okay, so that temperature, at particular temperature where the solid is going to change its crystalline form from one to another, so that particular temperature is called as transition temperature, and the process is called as transition process. Okay, so entropy change in transition process is calculated as delta S is equals to delta Ht divided by Tt, where delta Ht is the molar heat of transition in kilojoules per mole, and Tt is the transition temperature. Okay, so this is how So we are going to study the entropy change in 4 different physical processes. That is, one is entropy change in vaporization process, entropy change in sublimation process, entropy change in fusion process, and the last one, that is entropy change in transition process. Okay, so I am going to stop it here, and in my last class, in my next class, we will see about entropy of an ideal gas. So how we are going to derive our equation for entropy of an ideal gas, and further we will see entropy of a mixture of ideal gases, entropy change during mixing of ideal gases. So all these things we will discuss in my next class. Okay, so thank you, dear students.